Hello again, everyone, and welcome back once more to UNISEC Global's Mission Idea Contest lecture series. Today, Dr. Ozaki will present the fourth lecture in our series of 5 lectures to assist you with your mission design ideas for MIC7. Again, the lecture will run for approximately 60 minutes, but this time it will cover trajectory design for deep space exploration, a very important consideration for your mission ideas. Once again, we ask that you please use the chat function if you have any questions for Dr. Ozaki, and I'll curate those questions and present them to him. A Q&A period of approximately 15 minutes will be held after the lecture. And with that, I would like to introduce you to Dr. Ozaki. He's an assistant professor of JAXA, and he received his Ph.D. in 2018 in aerospace engineering from the University of Tokyo, working on trajectory optimization under uncertainties. His current research interests include trajectory design of spacecraft, robust optimal control theory, and small spacecraft. He's currently working on JAXA's Destiny Plus and MMX missions as a mission analysis expert. And he was also, although he hasn't asked me to mention this, the winner of the Young Researcher Award in the Conference on Space Science and Technology of the Japan Society for Aeronautical and Space Science in the 60th Space Science Technology Conference. Just so you know, hear a little bit about his background. I'm delighted to introduce you to Dr. Ozaki. This will be a fantastic lecture and will be a little bit different to the normal, as Dr. Ozaki has included some interactive elements. So with that, I'd like to hand it over to Dr. Ozaki. The floor is yours. Please proceed with the lecture.
Okay, thank you very much, Knight. And thank you for participating my lecture this time. So let me share the screen then. Okay. So can you see the screen?
We can indeed, clearly.
Can you also see this screen, by the way?
Yes, we can.
Okay, let's see. So I'd like to use this Quickest app. I'm gonna explain this later, but and then I try to make it very interactive session. So then, okay. So hello everyone. I'm Naoya Ozaki. As I might explain, but I'm an assistant professor of JAXA. So in this lecture, I'd like to present the trajectory design for the deep space exploration mission. And this background image is one of the trajectories that I designed. This is a trajectory of Destiny Plus, utilizing the electric propulsion and lunar swing by and solar tidal force. It's very, very complicated trajectory. So it's actually, this trajectory is just written in inertial frame, but this trajectory is the shape of trajectory is not elliptic anymore, and it's like a banana shape. And it's really complicated trajectory. But unfortunately, you cannot design this trajectory after this lecture. But after, if you study further, in the end, I think you can also design this type of trajectory. So this is just a brief overview of trajectory design. So I'd like to make this lecture is a starting point for you to start learning the trajectory optimization, trajectory design. Okay, so this is the self-introduction. Some of the, I think that not already talk about it a little bit, but I'm an assistant professor of JAXA, an astrodynamicist and space mission designer. So I got my bachelor and master degrees in the University of Tokyo under Professor Nakasuka and Professor Ryu Funase. Maybe most of you are familiar with both of them. And then I got my PhD in the University of Tokyo, and then during my PhD study, I also went to the ESA, European Space Agency, European Space Operations Center and the NASA JPL as a student trainee. And I studied the trajectory optimization in both agencies. And after that, I come to the JAXA ISAS, and then now assistant professor. So I participate in multiple small satellite mission, and then now I'm involved in some space mission, including MMX, Disney Plus, Comet Interceptor, which is upcoming JAXA's mission. Okay, so I'd like to use this Clickest app. So please access to this website and then try to use this Clickest. Okay, I'm gonna show you some test question now on, but the access to this Clickest app and enter respond and enter the code. The code is AYITQS. I always remind you every time I have questions, and I select A, B, C, D, and answer to the question. Okay. Okay, so let's go to the first test question using Clickest app. So this is the test question, so please relax. Okay, so what is the official name of Japanese Space Agency? So please select the right answer, A, B, C, D. Okay, I give you some minutes. Okay, access the Clickest and enter the code. The code is AYITQS. Okay. Okay, many of you answering, 17 people, 19. So the current is 37 people. So I think it, half of you already answered the question. So if you have any trouble, please let me know, let us know. Okay, 23rd people answered. So just to remind, so if you still not access to this website, try to access this clickest.net and enter respond and enter this code and select ABCD and select your answer. So 26 people answered to the question, 27, 8, 9, 30. Okay, I think it's almost most of you answered to the question, but let me share your answer. Okay, so yes, can you see the screen? So 25 out of 31 answer B. The other select A and D. And then the right answer is B. Japanese aerospace, so Japan Aerospace Exploration Agency. So actually the A is the old name of this Japanese space agency. And the B is current Japanese, the name of Japanese space agency, JAXA. And actually, this is also the question to evaluate your sense of humor. And only one of you answered to the D, but D is it's totally wrong. The question answer, sorry. Okay, so let's move to the lecture then. So this is the goal of this lecture. So the goal of this lecture is to be able to explain the role of trajectory design in deep space exploration missions. Second goal is to be able to explain what the form and transfer orbit, patched conics, and swing by. And the third goal is to understand a brief overview of advanced technique of astrodynamics. Okay, so this is the fundamentals of astrodynamics. So what is a trajectory design? So the trajectory design is to determine the route of spacecraft will take. So this is a sketch of a round trip trajectory, leave from the Earth and going to the moon and coming back to the Earth. So it's very simple trajectory. Some of the trajectory is very simple, but the other is very complicated. So this is one of the trajectory designed in a global trajectory optimization competition 8, GTOC 8. So there is some kind of global worldwide competition of this trajectory optimization. And then this is one of the solution of this GTOC 8 that I also participate in. So it's really, some of trajectory is really complicated, the other is very simple, but the essence is the same. So the important things in the trajectory design is evaluating the delta V, which is the velocity increment in the trajectory. So like velocity difference. So how do we gain this delta V, the velocity increment? I think you have already learned through the Professor Koizumi Sensei's lecture, but commonly used method is the rocket propulsion. So of course there is some other tricks I'm gonna explain later, but basically we gain the delta V using rocket and then control the trajectory. So how does a rocket work? It's basically the conservation of momentum. Okay. So if you throw a large mass backward very fast, you gain a large delta V from reaction. So it's basically the conservation of momentum. So how large mass we can carry using a rocket? So to answer to this question, we use the rocket equation. And I think you have already learned the rocket equations through the Professor Funase and Professor Koizumi's lecture. But I would like to know how many of you already know what rocket equation is. So please select the right answer from A, B, C, D using the quickest. So for the initial mass MI, final mass MF, and the specific impulse ISP, which rocket equation is correct? A, B, C, D. Okay. So I think please remember the Professor Funase and the Professor Koizumi's lecture. I think they have already told you. Okay, so I want to take a few minutes. So 6 people answer. 7, 8, 10. You can also change the answer if you want to change. Okay. So I think you have to remember the shape of this function of natural logarithm or exponential. Okay, 20 people answered the question. I want to wait a few more seconds. Okay, so okay, I want to see your answer. So how do you think? It's C. Many people say C, but A is also seems the correct answer, or D. Okay, so the correct answer is actually C. Okay, so if you forget which is the correct answer, please please check the Koizumi Sensei's lecture. I think he also derived these equations. But if you forget if you confuse which equation is correct, you should also try to remember the shape of this function of natural logarithm or exponential. So because MF must be smaller than MI, and MF is also must be positive. That is why the B is not the correct answer. A, D has the negative value. So considering this shape, C is right answer. Even if you don't know what the rocket equation is. Okay. So and then remember this shape of this curve. So for given initial mass Mi, larger MF is better, of course, which means you can carry a lot of mass to the target orbit. So how can we get the larger MF? To get the larger MF, make this number of ISP larger, or make smaller delta V. Either of these will get the larger MF, okay? And make larger ISP is a research topic of space propulsion specialist like Koizumi Sensei. And then make smaller delta V is a research topic of space mission designer like us. So we usually try to get the smaller delta V using trajectory optimization. Okay, so and then how do we calculate this amount of delta V? It's very simple actually, just calculate the difference of orbital velocity. So for example, this is example of example trajectory. So this green trajectory is initial trajectory and red trajectory is target trajectory. And then we want to transfer from this initial trajectory to this red one. To do this, we need to add delta V at this crossing point. So amount of delta V is evaluated just a very simple vector calculation. So if you have the initial velocity vector is 1, 0, and then the target velocity vector is 2, 1, the amount of delta V is just to take subtraction and take just evaluate the norm of this velocity difference. So in this case, it will be the square root of 2. It's very simple. Okay, so I think it's the calculating delta V is quite easy. But how do we calculate orbital velocity vector? So this is an essential difficulty of trajectory design. So this is one of the difficult part of trajectory design. Okay. But I want to explain how can we calculate the orbital velocity step by step from a very simple example. So let us calculate orbital velocity in a low Earth orbit. Okay. So this is the low Earth orbit. So this magenta trajectory is the low Earth orbit. In the low Earth orbit, the Earth's gravity and the centrifugal force balance each other. So we put the equation between these two, gravity and centrifugal force, and then solve for the V. Okay, and then you get this equation, and then substituting the actual number of gravity constant, the mass of the Earth, and the R is, for example, the radius of the Earth. Then the answer, the V, equals 7.9 kilometer per sec. So we call this is the first cosmic velocity. I think it's high school physics, so maybe many of you already know. But 7.9 kilometer per sec is necessary velocity to orbiting around the Earth. how about case to escape from the Earth? So to calculate the escape velocity, we evaluate we must solve this equation. The kinetic energy must be more than the potential energy of the Earth's gravity, and then solving this equation for V, you will get this equation. So substituting RGM, the same number as I explained before, we will get V equal more than 11.2 kilometer per sec. So we call that this is second cosmic velocity or escape velocity. Okay, remember it's 11.2 kilometer per sec. Okay, so let's use quick case again. Okay, calculate the velocity from low Earth orbit to deep space. Okay, so please remember the number that I explained. The first cosmic velocity and second cosmic velocity, escape velocity. Okay, and select which answer is correct. So if you want to leave from low Earth orbit to the deep space, how much delta V do you need? And then if you finish answering this question, please try to calculate the ratio of MF by MI using rocket equation. Here, for example, assume the ISP is 280 seconds. So this is a typical ISP number of solid rocket motor. Okay. So yeah, 11 people, 12 people answer. 13. Good. Good. Okay. So I think it's many of you have correct answers. So let me share the result. Okay. Okay. So this is the answer that you selected. So two people select A, one people select A, the other people select B, the other person select B, and most people select B. And the correct answer is D, 3.3 kilometer per sec. So just take a difference from 11.2 and the 7.9. Okay. And then if you also calculate this MF by MI using rocket equation, I think you will realize that the number is 0.3004. So which means you can carry the 30% of initial mass to the deep space from low Earth orbit. So which means, in other words, which means 70% of initial mass is just a propellant. So you know why the minimizing delta V is important, right? You know, the most of that is propellant. So the minimizing delta V is really significant problem for the mission design. Okay. Now, let's go to Mars. So this is another trajectory that I designed in JAXA. So this is JAXA's MMX trajectory. So MMX is a round trip mission from Earth to the Mars. So this is round trip trajectory, leave from Earth to going to the Mars and coming back to the Earth. So I think you can design this type of trajectory after this lecture. Okay, so now we call the Newton's law of universal gravitation. So in the vector form. So this is that equation of motion. So because we had the mass of the spacecraft m for the both side, we usually eliminate the mass of spacecraft here, and then we use this form of equation of motion. So hereafter we call that this is equation of motion of two-body problem. Okay. So for the analytical discussion, the conserved quantity is very, very important. It plays important roles. So hereafter, I'm gonna explain what is a conserved quantity and how can we calculate the conserved quantity from this equation of motion of two-body problem. Okay, so there is I'm gonna derive the two conserved quantity. One of that is angular momentum, the other is energy. There is also some other conserved quantity, but I don't explain this later. I don't explain this in this lecture, but if you are interested in, please check some books later. Okay. So because here is many equations, I fast forward most of this part, but please check it later and then try to derive this equation by yourself. Okay, so this is the equation of motion of two-body problem. So rewrite this equation using V equal dr dt, like this. And take a cross product of R from left side for the both sides, like this. And from the definition of cross product, the cross product of the same number is 0. So R cross R equals 0. So we get this equation. And using this relation can be derived using Leibniz rule of differentiation, yield this equation. So this equation means R cross V is time invariant, which means the constant. And then we define this R cross V. So H, we define the angular momentum H equals R cross V. And then finally, we obtain the conservation of angular momentum H equal R cross V is constant, time invariant. Okay, that's it. But this is very, very important because this is, we can derive the Kepler's law from Newton's law. So please try to calculate it by yourself later. It's very interesting and important data also. Let us derive another conservation of energy. Okay. First, okay, and rewrite the same way. And take a dot product of V for the both sides. And using this relation, yield this form. And manipulating a little bit, you finally get the defined the energy E equals this number, and it's time in this number is time invariant. So we obtain that the energy is constant. So in time invariant in trajectory. Okay, so we get the conservation of energy from equation of motion of two-body problem. Okay, so these two quantities very important. So, but okay, so this is summary of this conserved quantity of two-body problem. So we derive this conservation of angular momentum and conservation of energy. So I'm going to use these two equations from now on. So please remember this equation. So and then going back to the question from the transfer from Earth to Mars. So what is a transfer orbit that consumes minimum delta V fly from Earth to the Mars? So actually, actually, the minimum transfer orbit is like this kind of red trajectory. So the minimum delta V transfer is achieved when the spacecraft meet the planet in the opposite 180 degree positions. So we call this transfer is Hohmann transfer orbit. So to calculate delta V of this Hohmann transfer orbit, as I tell you, the important things is calculating velocity. So the first step is the calculating velocity at perihelion and aphelion. Okay, so this is an exercise of calculating perihelion and aphelion velocity of elliptic orbit. So given perihelion radius Rp and aphelion radius Ra, and find velocity Vp, perihelion velocity Vp and aphelion velocity Va from laws of conservation and angular momentum, conservation of energy and angular momentum. Okay, so if you have paper and pen, please try to solve this problem. Okay, so here is hint. So this energy conservation and angular momentum conservation is just as we derived. Okay, so using these two equations, please solve for the Vp and also Va. Okay, there is two unknown value, Va and Vp, and there are two equations. So you can solve this equation just using solving algebraic equation. Okay, so there is no quickest question here. But okay, so I'd like to explain this step by step. Okay, so we have energy conservation and angular momentum conservation here. And using this conservation, the first step is eliminating the Va. Okay, substituting this angular momentum equation to the energy equation. And then solve for Vp. You will get Vp equal square root of this. And then eliminating the Ra and the Ra minus Rp on the both sides, you will get the Vp equals square root of Gm divided by Rp and multiplied by the square root of 2Ra divided by Ra plus Rp. In the same way, you can also get the velocity at aphelion. That's it. So I think you can also calculate using this elliptic velocity using this energy conservation and angular momentum conservation. Okay, so now you know the velocity of Hohmann transfer orbit. Okay, and then so the velocity of the Earth and the velocity of the Mars is calculated using the same equation, or you can also calculate this the velocity of the Earth and Mars using the same way that we derived the first cosmic velocity, but you will get the same solution. Okay. So if you wanna arrive at Mars, the departure velocity from the Earth must be this. So this difference. Okay. So this is a related topic. I'm gonna explain that. I don't explain the detail of this Lambert problem, but I want to explain the brief overview of what is Lambert's problem. Okay, I didn't explain the detail, but the Hohmann transfer orbit assumed the Earth and Mars orbiting in a circular orbit, and also those two orbit is in the coplanar. But in reality, it's not. Especially the Mars orbit is quite elliptic. So solving this elliptic orbital transfer, we cannot simply use Hohmann transfer, but to do this, we need to use the Lambert's problem. Okay, so Lambert's problem is can be used to solve the initial velocity and the final velocity VI and VF when the RI initial position and terminal position RF and the time of flight is given. So I don't explain the detail of what is the Lambert's, so the theory behind the Lambert's problem, but if you are interested in the theory of Lambert's problem, please see this book or paper. Okay, it's a bit difficult to understand the whole process of this Lambert's problem, but it's really theoretical. Okay, but please understand that the Lambert's problem is a kind of function where the input is RI, RF, and time of flight, and the output is VI and VF. Okay, and then this Lambert's problem can be solved using some kind of numerical solver. And you can also access the open source Lambert's problem solver like a PyCap in Python. So using this PyCap solver, you can get this Lambert. You can solve this Lambert problem. So RI, RF, TOF, given RI, RF, TF, you can get VI and VF. So it's quite similar, same way as the Hohmann transfer. We get the perihelion velocity and aphelion velocity. But the Lambert problem we can solve in the elliptic or general case. Okay. So and another things I skip, but in the reality, we're considering that we have to consider the gravity of the Earth. Okay, I explained the Hohmann transfer orbit is like this kind of transfer, but in the reality, in the vicinity of the Earth, we cannot neglect the influence of Earth's gravity. And then in the vicinity of the Earth, the trajectory is becoming like this, like bending. So and then it becomes a hyperbolic orbit around the Earth. Okay. So to transfer from the Earth to the Mars, we have to consider this hyperbolic orbit part also. And then when the spacecraft reach to the some kind of velocity at the infinite point, so it's asymptotically converged to some kind of velocity. So we call this velocity V infinity or hyperbolic excess velocity. So this V infinity must be the one of the velocity difference that we calculated through the Hohmann transfer. Okay, so the what we calculated in the Hohmann transfer is not the delta V. So this is very important part. So it's not delta V, but it's V infinity during the Earth departure. Okay. So this type of approach is called patched conics. So this type of approximated design approach is called patched conics. So this red trajectory is simple elliptic elliptic orbit in two-body problem, and then this magenta trajectory is also neglecting the sun's gravity, but just consider the Earth's gravity, and then patch these two orbit. So this is patched conics. So to calculate the carriable mass to the Mars, we need to calculate delta V at departure at the Earth at this point. Okay, so what is a required delta V to escape from low Earth orbit to reach to the hyperbolic excess velocity being infinity? So let me show you how can we calculate this delta V at low Earth orbit. So from energy conservation, so we can also apply this energy conservation is in a hyperbolic orbit around the Earth. Okay, so this is energy conservation. Right-hand side is at infinity point. So that is why the R equals infinity. So this part becomes 0. And then solving this equation for the V0, we obtain this equation, the square root of V infinity square plus 2gm divided by R0. And then subtracting this velocity, or subtracting the initial circular orbital velocity, which can be calculated by square root of gme, the Earth's gravity constant, divided by R0, we obtain the departure velocity, delta V, by this form. So that's it. I think you can understand how can we calculate the Earth's departure delta V. And then this is the final exercise. I'm gonna explain it later. So if you solve this whole exercise, so this exercise is for calculating the carriable dry mass to Saturn from the Earth. Okay, so by solving this equation, I think you realize that using a 1.5 ton rocket, you can only carry the 105 kilogram mass to the Saturn. That this includes structural mass of rocket. Okay, so which means I think the payload mass might be the negative. Okay, so it means how hard to access to Saturn. So to access to the outer planet, that is why we usually use special technique of astrodynamics. Okay, so let's use the quickest. So what is a special technique to gain the energy to go to the outer planet or to get large energy from planet? So I think this technique is quite famous. So I think many of you may already heard about this name, but please answer, what is the name of a special technique for obtaining the large energy in astrodynamics? Okay, A, slingshot, B, swing by, C, gateway, D, gom gom bazooka. Okay, 8 people answer, 9. Yeah, I think since you get the more sense of humor. Okay, 16 people answer to the question. 17. Okay, 17 people and stopped. Let me show you the what did you answer. Okay, so this is the answer of you. So many people select C. Some people select A and B. Oh, more people select D. Okay, the right answer is the B, swing by. Okay, so I'm gonna explain what the swing by is. So I'm gonna explain the basics of swing by. So basically, swing by is based on the same phenomena as collision. So I mean the momentum conservation. The key point to understand swing by is the reference frame. Okay, so in the Earth's relative frame, the spacecraft orbit in hyperbolic orbit. It's very simple hyperbolic orbit. Okay, like incoming velocity and then the outgoing velocity is the same. These two incoming and outgoing velocity is the same. So there is no energy increment in this the hyperbolic velocity. But if you look at the spacecraft velocity in the inertial frame, we also have to consider the Earth velocity in this inertial frame. So the spacecraft velocity is in the inertial frame is the sum of this green and blue vectors, which means these red vectors for both sides. So if you look at these two figures, you can easily figure out that the Earth spacecraft velocity in the inertial frame increased significantly. Okay, so this is the basics of fundamentals of swing by. So swing by, so we use swing by to gain the energy, and sometimes we also use the swing by to reduce the energy. Okay, so so far I have explained the fundamentals of astrodynamics technique, but from now on I'd like to explain the brief overview of advanced technique of astrodynamics. So there is many astrodynamic techniques can be used in cislunar region. I mean the Earth and Moon region. For example, moon swing by, or we can also use solar tidal force, or there is a Lagrange point or halo orbit, or we can also use invariant manifold technique around the halo orbit. So I just listed up the keyword. So please check these keywords later. But I want to mention that there is many technique can be used in this cislunar region, and I want to explain that one of this technique important knowledge from now on. Okay, so for the deep space mission, I think using a small satellite, small spacecraft, I think Lunar Orbital Platform Gateway will be very, very important in these upcoming years. So where the Lunar Orbital Platform Gateway is? So Gateway is orbiting around the near rectilinear halo orbit around the Moon. So unfortunately, I cannot explain what near rectilinear halo orbit in this lecture, but it's the type of the orbit influenced by the Earth's gravity and also Moon's gravity. So this is not just an elliptic orbit around the Moon. So it's this near rectilinear halo orbit is a type of halo orbit which is affected by both Earth and Moon's gravity. So to understand this near rectilinear halo orbit, we have to understand what the Lagrange point. So Lagrange point is equilibrium point where the Earth's gravity and Moon's gravity and the centrifugal force balance each other, like this. So let us start from equation of motion of three-body problem. Okay, and then I would like to explain the equation of motion of circular restricted three-body problem. So this is generic equation of motion of three-body problem in inertial frame. So the difference from the equation of motion of two-body problem is this just the second term of right-hand side. Okay, so solving this equation is a bit difficult and tricky, and then we cannot solve this equation analytically. But if we assume the two things, the one is restricted assumption, the other is circular assumption, then we can discuss something in an analytical way. Okay, the restricted assumption is the spacecraft mass, spacecraft gravity does not affect both Earth and Moon, the primary and secondary body. And a circular assumption is both primary and secondary bodies moving in a circular orbit around the body center of this. Okay, and then putting this assumption and then transform this equation of motion in the rotating coordinate system, we can get this type of equation of motion. So I didn't explain the detail of how can we derive this equation of motion, but if you are interested in, please see the literature that I'm gonna show you later. But if we want to find the Lagrange point, we just use the dynamical system theory technique to calculate equilibrium point. So how to do this is just eliminate the time derivative of the state x, y, z. So just eliminating all of these terms, and then calculate this omega x, omega y, omega z. So this is partial derivative of omega with respect to x, y, z equals 0. So as you can see, it seems like it's easily solved, and I think you can also solve it by yourself. Okay, so then I'd like to move on to the quickest question. So I think Lagrange point is also the famous, one of the famous term. So please select the answer to this question. How many Lagrange points exist in the CR3BP? I want to know how many of you already familiar with Lagrange points. Okay, 7 people, 8 people answer, 9, 10, 11, 12, 13. Okay. Okay, 19 people, 20 people answer to this question. Okay, so let me show you the answer of your answer. So many people select C, some people select B. Okay. But actually, the correct answer is C, the 5. So I strongly suggest you to calculate this Lagrange point by yourself, and you get there is 5 Lagrange points exist. Okay, so there is 5 Lagrange points exist in any CR3BP system. And then there's 1, 2, 3, 4, 5 Lagrange points exist. But again, this Lagrange point exists in any CR3BP. So if you mention the Lagrange point, you also have to mention in which system. Okay, some people just say that the L1 Lagrange point, but where? I mean, in which system is important. Sometimes the people may mention Earth, Moon, L1 Lagrange point. The other time people mention the Sun, Earth, L1 Lagrange point. So it's important to mention in which system. And also, it's only exists in CR3BP, so it's ideal system. So in a realistic system, as I tell you, Earth is orbiting in an elliptic orbit, for example, the Lagrange point doesn't exist. So the Lagrange point that is why it's just ideal things. So in the reality, it's so exactly, strictly speaking, Lagrange point doesn't exist in the Sun-Earth system. Okay, and this is basic the sketch of geometry of Lagrange point. There is the Lagrange point exists in the Earth-Moon system, 1, 2, 3, 4, 5, and then this 5 Lagrange point rotating. And then there is also the this sketch is written in the Sun-Earth line fixed rotational frame. Okay, so the Earth is center and the Sun is always in the left side. Then in a cislunar region, there is also the Lagrange point of the Sun-Earth system. L1 Lagrange point, L2 Lagrange point are very close to the cislunar region. And the gateway will be constructed in this L2 Lagrange point of Earth-Moon system. Okay, it's not Sun-Earth L1 Lagrange point, but Earth-Moon L2 Lagrange point. Okay, so I couldn't explain all of these techniques in this lecture, but if you are interested in, please check these keywords or read the literature. But as for the simple mission design or brief mission design or system design, maybe you can also use this kind of delta V information, or we sometimes call delta V map. If you Google delta V map, you can also get a similar type of delta V map to transfer to another system. But this is the delta V map or related to the gateway mission that I calculated. So it's just a brief number, rough number. So if you can just use the rough estimate of transfer from gateway to the other type of orbit using this delta V map. For the accurate calculation, you need to calculate by yourself using a special technique like periodic invariant manifold or low-slash trajectory optimization. But for the very simple brief analysis, you can start using this type of delta V map. Okay, here is conclusion. So this is the goal of this lecture that I explained in the beginning, to be able to explain the role of trajectory design in the deep space exploration mission. And the second objective, second goal is to be able to explain what the Hohmann transfer orbit, patched conics, and things by these. And the third goal is to understand the brief overview of advanced technique of astrodynamics. And I explained the Lagrange point and another advanced technique. The keyword of another advanced technique. So for those who want to know more, please check these book, these keyword, and also please check these tools. It's very, I think, convenient for your mission design. That's it. And then here is the exercise. If you have paper and pen, if you have a time, please try to solve this exercise 1, 2, 3. And I also attach the answer to this exercise, so you can also check the answer of this exercise later. Okay, so thank you very much for your kind attention.
Wow, thank you very much, Ozaki-sensei. That's fantastic. I think we've already got actually somebody in the audience who's giving you applause, which is nice to see. And look, the references you included in the clickers questions did not get past me at all. I couldn't help myself but respond to both of those sense of humor ones. That was fantastic. I would now like to open up the floor to the attendees. If you do have questions for Ozaki-sensei, please post them in the chat. We have had a few questions coming in, so we may start with one from Kevin, who asks, in actual mission design, do you first solve problems using Pickett, the program, and then verify your solution manually, or do you do it the other way around? What's your approach?
Okay, so yeah, really good questions. So it's totally depend on the it's totally depend on the problem. Okay, so but in many cases we use the numerical method first, and then to get the confidence of this numerical result, we use this kind of analytical evaluation. So especially one of the important things is, for example, that if you, so for example, if you had small amount of delta V, but you change, you get a lot of energy change, maybe you made a mistake in some part. So then we check it, the program source code written by myself date, and then debug whether there is wrong or not. So usually like this kind of way.
I see.
But sometimes, for example, in the case of
sorry, continue.
Sometimes
no,
in the case
go
of,
ahead.
for example, this the case of, for example, the Earth to Saturn in this example, for example, sometimes I just start using this analytical expression first and evaluating the how many mass we can carry. And then if this result is totally infeasible, then we have to change the whole direction completely. So that is why it's totally depend on the problem and what kind of mission design we want to do.
I see. So you might just do a quick verification first to see if it's actually worthwhile exploring at all, or otherwise it's a bit of wasted effort, isn't it? Yeah.
Exactly.
When you're performing numerical analysis on these trajectories, though, what type of precision are you looking for in the solutions that you're actually having returned?
As precision, you mean the precision of like numerical precision?
The numerical precision in the result that you're obtaining when you're actually solving for these trajectories. What type of precision are you often aiming for?
Okay, so this is also very important question, and then I think we need a lot of sense of mission designer. For example, I show you this delta V map, and this is very you can use this as a rough estimate, but this precision is really bad. And then I also explained that the patched conics approach, but this patched conics approach is also approximation. And then patched conics approach. So that is why in actual mission we have to solve the high fidelity problem, not just a patched conics assumption. So we really need a sense of mission designer to which precision we need, but it's really difficult to say that in in a generic case. But for example, in Earth-Mars transfer, we can simply use patched conics assumption. But for example, in the transfer in a cislunar region, patched conics is not a good approach, because
right,
the moon's gravity is really large, and also the sun's gravity, as I explained here, the moon's gravity is not small, and also the sun's gravity is also involved in the this cislunar type of trajectory. That is why the patched conics or Lambert problem might not be a good method to approximate trajectory.
Right.
So
Yeah.
it's depend on that type of problem. Yeah.
Yeah, of course.
But
it also, I suppose, it depends
that
on the distance you're going as well, doesn't it?
Yeah, that is true. And also how much margin you have is also important. So if you have a lot of delta V margin, maybe this difference is negligible. So
I see. Well, thank you very much. That was a very detailed response. We had a question from Uriel, who asked, is the Hohmann transfer only applied to 2 orbits around a central body within the same plane, or is it possible to apply it for 2 orbits in different planes?
Okay, yeah, good question. Okay, so the similar type of approach. So yeah, so that we call Hohmann transfer orbit is only consider that these 2, Earth and Mars, is in the same orbit, same plane, but the similar type of analytical method can also use for the plane change too, actually. So in the case of plane change, if you want to change the plane, it's better to change the plane in aphelion. So if the two, so the one of the approach to calculating the orbital transfer considering the plane change is just consider to change the plane in the aphelion by adding delta V at aphelion. Okay, so but the difficult point of this, if the 2 orbit, the plane of these 2 planet in the difference, the difficult things is that you can only yeah, so the difficult things is if you leave Earth, and then if the Earth orbit and this spacecraft orbit in the same orbit, the same plane, and then if the Mars is in a different orbit, then spacecraft cannot reach to the Mars except the Mars is crossing at this point, at this plane. So you have to consider in a 3D. Okay, so that is why I recommend you. So if you want to consider the plane of this Mars and Earth is different, I strongly recommend to use this Lambert problem instead of using a Hohmann transfer. So that is why, for example, in the actual mission design of this, for example, the MMX, this is actual mission, and I explained the Earth and Mars, the plane of Earth and Mars is different. The Hohmann transfer can be used as rough estimate of this Earth-Mars transfer, very, very rough estimate. but the Lambert problem can use as much more accurate result. And also in the case of MMX trajectory design, we can also use Lambert problem. And I also use Lambert problem in this trajectory design.
I see. So just to recap, you need to use the Lambert problem, and you need to also consider the point at which there's actually a crossing of the plane.
Yeah.
Okay, excellent. Thank you very much. We had a question from Min, who asks, is there a different approach if you're designing a trajectory using an electric propulsion system? And then a follow-up to that, Min asks, do you use any software to simulate the trajectory?
Yeah, okay. So I completely skipped the trajectory design using electric propulsion, but this low thrust trajectory design is very, very difficult compared to the ballistic trajectory design. So to design the low thrust trajectory, you need to solve trajectory optimization problem, because there is so many decision but control variable parameter or decision variable. You know, you can change the magnitude of low thrust or electric propulsion, and also you can change direction of electric propulsion in any moment, right? So it's so many decision parameter. So you have to use nonlinear optimization technique. So I think I listed up here. So if you want to know how can we solve the trajectory optimization using electric propulsion, I strongly recommend you to read this paper, this book of John Betts, Practical Method for the Optimal Control using Nonlinear Programming. So you need to solve the nonlinear programming, or NLP. Yeah, but maybe you can use the software like the PyMo or EMTG. I think it's include the low thrust trajectory design solver. But if you are studying trajectory design, I recommend you to implement by yourself. It's not that difficult. I mean, as a researcher, it's not that difficult. So I think it's really good to understand how the low thrust trajectory optimization work. So, and then another question is, do you software? Any software? Yeah, software is, I think, these software, or please check the keyword of direct trajectory optimization method, or multiple shooting is, I think, the keyword.
All right, I think that book is probably something many of our attendees would like to take note of. That might be a common theme, I think, that arises. We have a question from Christian, who actually is asking about multi-body problems. So as an example, doing something in the asteroid belt, where you have, how do you model the dynamics where you have several objects with a mass closer to the spacecraft mass? Is the patch method too complicated? Do you rely mainly on codes or simulations, or how do you approach a situation like that?
Okay, yeah, okay. So yeah, so the basically the asteroid mission. So in the vicinity of the asteroid, of course, you have to consider the asteroid gravity. Like, for example, Hayabusa 2 mission, you have to consider the gravity of the Ryugu or Itokawa. But the other case, you don't have to consider the asteroid gravity because it's really small and it doesn't affect. So for example, if you go to the main belt, you don't have to consider the gravity of whole main belt asteroid. You just consider the asteroid of where you're gonna go. So, but the problem of this asteroid mission is the gravity model is really difficult. So this gravity model that I explained is, I also skipped the detail, but this gravity model, we just assume that the Earth and Moon is just a point mass. Okay, but in reality, the Earth and Moon is not point mass, but it's has huge volume. But if the shape of this mass is a sphere, then you can assume that if this body is sphere and a uniform mass distribution, then you can just assume as a point mass. So there is theory behind, and I skip, but just you can assume it's point mass. But in reality, it's not, right? So, and especially in the case of asteroid, the shape is very awkward, and also the density is also it's not uniform. So for those cases, we have to consider the very difficult gravity model of asteroid. So the high fidelity gravity model is also a hot research topic in astrodynamics. Some technique use approximate gravity model using a spherical harmonics expansion. The other is assume the kind of polygon of bodies.
I see. There you go. And so if you're an aspiring astrophysicist who wants to work on trajectories, that might be an area of interest for some of our attendees to pursue.
Yeah. And then also, and then the patched method is, to answer to this question, so for those complicated gravity problems, we cannot use these kind of simple analysis also. So we have to rely on the code or numerical method. But again, so as a rough estimate, we can use analytical method like I explained here. Okay, so the usual step maybe related to the first question but the usual step is designing the rough trajectory using analytical approach, and then using this analytical trajectory as the kind of initial guess of trajectory, and then using numerical method to define this trajectory. So this is what I usually doing.
I see. All right, thank you very much for the response to that question, Ozaki-sensei. And we do have another question here from Ying. This may possibly be our last one. So if you do have any other questions, our attendees, I encourage you to post them now. But Ying asks, what do we need to consider for mission trajectories involving touching? For example, like Hayabusa 2, landing or impacting on the target.
Okay, so touchdown. Well, for example, touchdown on the asteroid, or where if the touchdown on the Mars is, I think it's completely different problem because we have to consider the atmosphere of the Mars. But basically, so we usually divide the whole mission phase into the several separated phase. Okay, so in the case of Hayabusa 2, for example, we divided by the one of the phase is interplanetary cruise. So using electric propulsion, and then once the Hayabusa 2 arrive Ryugu, it's going to the another phase, another separated phase, like the asteroid vicinity approximate operation phase. And in this phase, we have to consider the high fidelity of asteroid gravity. But for example, in this trajectory, we don't have to consider the Earth's gravity or Moon's gravity. We just simply consider the Sun and high fidelity asteroid gravity. So we can divide, like, the mission phase into the more smaller package. So in the case of touchdown trajectory design, so we just consider the asteroid gravity and solar perturbation, and also maybe you have to consider the acceleration from solar radiation pressure, which is come from a photon of the sun, but including those perturbation, and then solving a touchdown trajectory to the asteroid.
Understood. That makes sense. Make it much easier to manage everything, that's for sure. I don't know what other approach you would use, to be honest, thinking about it. I'd like to ask our attendees, if you do have any other questions, please post them now. We are reaching the end of the Q&A period. Okay, I think we may have reached the end of the questions there. So I'd like to just thank you once again, Ozaki Sensei. That was brilliant. And I think that adding the interactive elements as well made that very special. So please, attendees, if you can join me in thanking Dr. Ozaki for his time this evening, that'd be fantastic. And we will be uploading the video of this presentation as well as a copy of his slides to the website soon. And we're also very fortunate that Ozaki Sensei has included some excellent exercises for you to complete. So just to remind you once again, abstract submissions are due on the 7th of July. I know I've said it for a few times now in a few of the sessions, but you do need to start considering writing your abstract if you haven't already. And one thing that I'd actually like to point out is that when you are writing your abstracts, some of the considerations for that submission above the evaluation criteria that we reviewed last week would be to consider how your proposal may satisfy the United Nations Sustainable Development Goals. UNISEC Global is actually a permanent observer of the Committee on the Peaceful Uses of Outer Space. And as such, incorporating these principles into your mission idea will be well regarded in the selection process. In addition, I'd also like to suggest that you look at how your mission idea may contribute to creating a world where university students can participate in practical space projects in all countries and regions by 2030, which is part of UNISEC Global's Vision 2030 All initiative. Now, I'd like to also just update you on our lecture schedule. So we have had a change in the schedule for the delivery of the last lecture. And although we do want to deliver all the necessary components to you for your abstract submissions as soon as possible, we are having to delay the next lecture. It's going to be moved until to March 18th. The lecturer has had a few commitments which he's unfortunately had to delay for. But you can use this as an opportunity for some private study time before that last lecture. And you can also use this to review the last lectures as well as to complete Ozaki Sensei's exercises, which he has most kindly left for you. So we do hope that your mission idea is on course for submission soon. We will notify you when we open that up officially. But I'd like to also remind you once again, please download the abstract template if you haven't already. There is a detailed guide as well on the website about how to submit an abstract and what you should include in it. And to conclude the meeting, I'd like to thank you all once again for attending. And we look forward to seeing you on March 18 for Tomiki Sensei's Communicating for Deep Space Missions with Micro Nano Satellites. Once again, please join me in thanking Ozaki Sensei for his time, and we hope to see you at the next one. Bye for now.